All right, we've seen triple integrals and we've also seen double integrals in the one curved coordinate system that we want to investigate here, which was polar coordinates. It's now time to take a look at triple integrals in curved coordinate systems, and the two curved coordinate systems that we are going to look at in this course are cylindrical coordinates and spherical coordinates. For both presentations, we're going to basically go through this informal / physical interpretation, which is that a triple integral is a sum of little numbers multiplied with small volume elements. And so for both derivations of the formulas, we need to figure out what the shape of the volume element is and what the volume of the volume element is. And in fact, that's what we will start with. So, quick introduction one more time. In 2 dimensions, we've already seen that rectangular coordinates aren't terribly well suited to integrate over round objects, right? That's why we looked at polar coordinates. And so now in 3 dimensions, we want to do the same thing. For axisymmetric objects, for turn components, for volumes of revolution, basically, cylindrical coordinates ought to be a good choice. And for anything that's spherically symmetric, which is spheres and pieces of spheres, spherical coordinates ought to work well. And so the big thing, like I also mentioned, the big thing that we have to figure out is what the volume elements look like. So let's remember, cylindrical coordinates are nothing but polar coordinates with a z, and just as in polar coordinates, the area element basically was what we got if we took a little step in each of the coordinate directions, where one of the directions was an angle. We would do the same thing in 3 dimensions also. If we take a little step in the radius, a little step in the angle theta, and a little step in z, we get something that sort of looks like a box, not quite, because there are some round boundaries, but with this 3D picture, of course, we can also see that this quote-unquote mantra of calculus, that when you focus in far enough, things become bounded by straight lines, that certainly holds true here, because if we look at one individual little shape here, that looks very much like a box if we didn't have the perspective that the sides aren't completely parallel. We would even be tempted to say that that really is a box. In terms of measuring it, well, let's just take a look at it. Take an XYZ right-handed coordinate system, and, well, we know that a little step in theta would be a step d theta that happens in the XY plane, right? And when that happens, you get a little area element, which is just like the area element in polar coordinates, and that is, of course, quite natural, because, after all, cylindrical coordinates are polar coordinates with z. And then, because of the z, of course, a volume element in cylindrical coordinates would be standing in space, and basically you would be at a point like this one here, and then you would have a little volume element that looks like this, where the vertical thickness is dz, where the length of this side is dr, a little step in the radius, and the little step d theta, that'll be r times d theta for this length here, because, after all, again, we're looking for a volume element, and so if we do a unit check here, this is a length, this is a length, and this is a length also, because theta in radians is, of course, dimensionless. And if you multiply 3 lengths with each other, you get a volume. So again, this is a very physical way of reasoning, and that's not a bad way of reasoning this out. So the volume element, the differential volume element in cylindrical coordinates would be dv, and that would be r times d theta times dr times dz, which is exactly the 3 lengths that we get if we take a differential step in each of the coordinate directions, where the direction may need to be put into quotation marks because the theta direction is not quite a direction here, right? So the theorem overall then is, if you've got f of x, y, z, and that's integrable over a cylindrical region R, which is given by the radius being between a and b, the angle theta being between alpha and beta, and the height being between g and h, then the integral of f over the region R is the triple integral of f over the region R dv, and that'll be the integral from alpha to beta in theta, the integral from a to b in R, and the integral from g to h in z. we would have f of x, y, z, where x is replaced with a corresponding cylindrical quantity r cosine theta, y is replaced with a corresponding cylindrical quantity r sine theta, z is of course still z, and then we have r dz dr d theta. That whole thing is basically replacing the dv, so this is what previously was dx dy dz, that is now r dr d theta dz in any order that you want, really. Okay, and so now let's take a look at some examples. I want to integrate the function f of x, y, z equals x squared plus y squared over the region that is bounded by the paraboloid z equals x squared plus y squared and by the plane z equals 3. And this time I think this one I want to integrate using the sandwich method, but either way, we've got a paraboloid, we have a plane at height 3, and therefore the region that we want to integrate over is this thing here. And so that would mean, first of all, I need to figure out my base. And if x squared plus y squared is equal to 3, well, that means that r squared is equal to 3, and that means that the radius is square root of 3. So that means that my radius here, as I want to do this with a sandwich method where I'm going from the blue paraboloid to the orange plane in z, my radius would have to go from 0 to root 3. Then I have x squared plus y squared is less than or equal than z, which in turn is less than or equal than 3, because after all we want to go from x squared plus y squared to 3 here, right? And so that would be that r squared is less than or equal, z is less than or equal than 3. And we've got theta, well, it goes all the way around, so theta goes from 0 to 2 pi. So that means that the integral is the integral from 0 to 2 pi, that's the theta integral. Integral from 0 to root 3, that's the r integral, and then integral from r squared to 3, that's the z integral, of our integrand, which is x squared plus y squared, which is r squared, times the volume element, and the volume element is r. I'm not sure if I can highlight that here. The volume element starts with the r, and then is r dz dr d theta here. And so that is essentially a sandwich method, right? Because dr d theta encodes the base, and then the bottom of the sandwich is the r squared, and the top of the sandwich is the 3. And so that's also one where we don't just have everything start at 0, which is a nice example to show that the integrals don't always have to start at 0. Either way, the rest is just computation. So first of all, we realize that r squared times r is r cubed. Everything else stays the same. And if I integrate r cubed dz, well, that's just multiplying the r cubed with 3 minus r squared, right? So I keep my outer integral from 0 to 2 pi and from 0 to root 3. I keep my r cubed integral of dz from r squared to 3 is just 3 minus r squared. Keep the dr, keep the d theta. And so then I multiply that out. So this is still the same outer integral, 3r cubed minus r squared times r cubed, which is r to the 5th. Now I'm integrating dr, so I get 3/4 r to the 4th minus 1/6 r to the 6th, right? Okay, so integral 0 to 2 pi d theta stays because that's the outer integral. 3/4 r to the 4th minus 1/6 r to the 6th from 0 to root 3. All right, at r equals 0, we don't get anything. Root 3 to the 4th is a 9, so we end up with 27 over 4. And then root 3 to the 6th. Wait. Root 3 to the 4th. Yeah, 27 over 4 is right. Root 3 to the 6th. Well, let's see. Root 3 squared gives me a 3 that cancels, so we end up with 9 halves here. 27 over 4 minus 9 halves should be what we get there. Yes. Integral 0 to 2, 27 over 4 minus 9 halves. 27 over 4 minus 9 halves should be 9 over 4, because that's 18 over 4 here in the back. Okay, integral 0 to 2 pi, 9 over 4 d theta. And that ends up being 9 halves pi then. Okay, so you can see the computation isn't that bad, and that certainly isn't a computation that I would have enjoyed doing in rectangular coordinates, because first of all, the encoding of the circle would have been rather rough, and then I would have had all sorts of more or less ugly integrals that would have probably made it worse. Okay, let's also take a look at how we would use the axis method here. So let's take a turn component, so that would be a volume of revolution, and the radius of that turn component is given by r equals z squared. and that is for z between 0 and 2, and I want to integrate the function f of xyz equals z over this volume. So this could be part of maybe a computation of the center of mass, where ultimately you would have to integrate z. However, it is not the center of mass itself because I don't have the 1 over m in here. Either way, r equals z squared. Here's, of course, where the visualization is really important. R equals z squared. If you graph z versus r, then z is square root of r. So this is not a paraboloid. This is actually something that has a very sharp tip. It's an object that looks like this. This is r equals z squared. Here's the plane z equals 2. That's where the object is capped off. So it's like a very sharp spinning top type thing. And we would still want to know how to integrate over that. And what can we see here? Well, z would go from 0 to 2, and then we have to figure out what those circles are, right? So for those circles, theta goes from 0 to 2 pi. Z goes from 0 to 2, like I just mentioned. And the radius, well, the radius goes from 0 to z squared. And that would give us that our integral goes from 0 to 2 pi, from 0 to 2, and from 0 to z squared of z, r dr dz d theta, and we did that in an order that is not quite how the axis method would work, but you can clearly see here that whether I make my dz my second integral or my outer integral, it works the same way. So another thing that we can file away is that we don't necessarily need to apply the method mechanically. We used the axis method to get the inspiration for what the bounds are, and once we realized that there's only an r dependence on z, we could set that up in any order that respects that r depends on z, meaning in any order where the r integral is inside the z integral. Either way, this is the integral. The rest is, of course, just computation, and so we would take that integral, and if I integrate with respect to r, I would get z times 1/2 r squared, right? So I keep the outer integral, 0 to 2 pi, 0 to 2 from right here. I keep my dz d theta, keep my z, antiderivative of r is 1/2 r squared, going from 0 to z squared, giving us 1/2 z to the 4th times z, so that would be 1/2 z to the 5th, right? And we can take the 1/2 out, so get 1/2, outer integral stay the same, we have the z to the 5th dz d theta. Of course, the integral of z to the 5th is 1/6 z to the 6th, so we end up with, keep the 1/2, keep the outer integral, 1/6 z to the 6th from 0 to 2. Let's see, two of those 2's cancel, one with the 1/2 and one with the 2 that's in the 6. We end up with 1/3 2 to the 4th, so that would be 16/3 if I'm not completely wrong. Yeah, 16/3, and of course that can be pulled out, and we have an integral from 0 to 2 pi d theta, which just gives us 32 pi over 3, and that is the answer. Okay, now note this is something that we would use as a step towards the center of mass. It's not the z-coordinate of the center of mass because I haven't divided by the volume here if we were to assume that it's constant density 1. Alright, let's take a look at spherical coordinates. Well, again, first we need to have the integral formula, and basically, again, volume elements, remember volume elements are when you take a step in each of the coordinate directions. So you take a small step in the radius rho, you take a small step in the angle theta, and you take a small step in the angle phi, which comes off the z-axis. And again, we can see in this picture very nicely that if these steps are small enough, then the little volumes that you get really look like little boxes, so that's very nice. But we certainly need to figure out what the lengths, the side lengths of those little boxes are. A quick unit check tells us that d rho, d theta, d phi is not going to be the right volume element because rho has a length unit, theta and phi are dimensionless, and so that would mean that we would have a volume that is measured in length units, and that is incorrect. So we have to go back to drawing our xyz right-handed coordinate system, and then we know that at a point here, r theta phi, we could attach a little volume element where we're taking a little step in rho, a little step in phi, and a little step in theta. And well, as we do that, we certainly then see what this thing ought to look like, and we already see also that one of the dimensions will be just a d rho. In order to get this dimension, we realize that, of course, the angle phi comes off the z-axis. So there's a little d phi here, and that means this length here will be rho times d phi, just from the definition of radian measure. And that leaves us with this little length here, but we have to remember that this is basically something that we project down. And then this length here is this length here. And if we go towards the center, we realize this little angle is d theta, and that means that this length here is r d theta. And so basically we have that r is rho sine phi, so this is rho sine phi d theta. If you want to work that out by hand one more time, what would you do? You would have that phi comes off the z-axis, which means phi is also the angle between the vertical and the connecting line here. And then we have a right triangle, so that means d theta over rho is sine of phi, and that means that this length here, is rho times sine phi, because this length over rho is sine phi, so this length is rho sine phi, and then you have to take this length and multiply it with the d theta. Overall, that means that our length up here is rho sine phi d theta, and that means that if f of x, y, z is integral over the spherical region R, that is given by rho between a and b, theta between alpha and beta, and phi being between gamma and delta, then the integral of f over that region is triple integral of f over the region dv, being integral from alpha to beta in theta, integral from a to b in rho, integral from gamma to delta in phi, and then our volume element dv is the rho sine phi d theta, rho d phi d rho, which is rho squared sine phi d phi d rho d theta. So this here is the volume element dv, and even though I often say you want to have the visualization because you can derive everything from that, I certainly recommend to memorize this volume element because we will need it quite frequently. And then what we have already seen for the cylindrical coordinates, x, y, and z are being replaced by their corresponding spherical counterparts, which are rho cosine theta sine phi for x, rho sine theta sine phi for y, and rho cosine phi for z. Sorry about the highlighting here, that just sometimes just jumps over, as you've already seen frequently in presentations. Either way, this is how we would set up the integral. And so now, as an example, let us integrate the function f of x, y, z equals x squared plus y squared plus z squared over the top half of the solid ball of radius 2 that is centered at the origin. Well, that is something we ought to be able to visualize in our heads, but nonetheless, here's the picture. It's the top half of a solid ball centered at the origin of radius 2. What would we do? We would integrate from 0 to 2 pi in theta, because we have to go all the way around. Remember, phi comes off the z-axis, and so it starts with phi equals 0 and goes a quarter turn, so phi would go from 0 to pi over 2. And then the radius would go from 0 to 2, of course, because the thing has radius 2, as we can see here, because that's a 2, which lines up exactly with the furthest extent that this hemisphere has. F of x, y, z is, of course, rho squared. Then we've got rho squared sine phi d theta, d rho d phi d theta, which is exactly the volume element. And, well, the rest is just computation, and in fact the computation isn't that bad, because everything decomposes, right? We have that nothing depends on theta, so we get that the integral with respect to d theta is just multiplied with all the other stuff. Then we've got only sine phi depends on phi, which means we can factor out the integral with respect to d phi, and we get integral 0 to pi over 2 sine phi d phi. And rho squared, well, that's rho to the 4th, and so we end up with the integral 0 to 2 rho to the 4th d rho here. Those can all be computed separately, so we get 2 pi here, we get negative cosine phi from 0 to pi over 2, and we get 1/5 rho to the 5th from 0 to 2. Exactly. And so we've got the 2 pi there. This integral here, let's see, cosine of pi over 2 is 0, and cosine of cosine of 0 is 1, and so 0 minus -1 gives us a 1, and 2 to the 5th is 32, so we get 32/5 here minus 0 as the last one, so we end up with 2 pi times 1 times 32/5, which is 64/5 pi, and that's it for that computation, right? So we just look at the ball and visualize and then set up the integral. Another example, if we have one of these iterated integrals that looks rather ugly in rectangular coordinates, well, that is one where changing the order of integration isn't going to help much. However, if we look at this, x goes from 0 to 3, and then y goes from -√9 minus x squared to 0. So -√9 minus x squared, that would be the lower half of a circle of radius 3, and then because we only go with x from 0 to 3, that would be a quarter circle, and it would be a quarter circle in the fourth quadrant because x is positive and y is negative. And the integral from 0 to square root 9 minus x squared minus y squared, well, that is just the integral from 0 to a hemisphere. And so basically this thing actually looks like this. And that's the kind of thing that we can then also visualize. And basically, as I've talked you through that, I hope you already saw a shape like this in your mind, because that's what you want to do if you can't draw this too well, and I wouldn't blame you if you can't freehand this terribly well, because that is actually quite challenging to do. But basically, what you would have, or hopefully have seen in your mind, is if you look at this thing from above, then of course you have to rotate it so that the x-axis actually goes across. And when you do that, as I'm rotating here, when you do that, well, here's what you can see when you do that. Okay, and so now we have this object rotated in such a way that we're looking straight down the z-axis, and we can see that, yes, the x-axis goes across. I didn't want to keep pushing here. The y-axis goes down, so that means that our theta angle will go from -pi/2 to 0, or from 3pi/2 to 2pi, and then the radius would go from 0 to 2, and of course our phi angle, because phi comes off the z-axis, phi would still go from 0 to 2pi, because independent of which quadrant we're in, phi always comes off the z-axis in the same fashion. Alright, so that means in this thing here, we would now have that the radius goes from 0 to 3, actually. Okay, I'm not sure, did I have the right piece there? Yeah, it went to 3. Alright, so that was just making sure I had the right visual there. Okay, so radius goes from 0 to 3. Sure, it's because the whole thing has radius 3. And then theta I chose to let go from -pi/2 to 0, and phi goes from 0 to pi/2 as we have seen. So that means the rest now is just computation, because now we just set up the integral. The integral of this y is the same as letting rho go from 0 to 3, phi go from 0 to pi/2, theta go from -pi/2 to 0, y would be rho sine theta sine phi, and then we keep the volume element, which is rho squared sine phi times d theta d phi d rho, which is lining up correctly here. Okay, so that would give us the integral from 0 to 3 of rho cubed d rho, because we've got rho and rho cubed, and none of the other stuff depends on rho, times the integral from -pi/2 to 0 sine theta d theta, because only the sine theta depends on theta, times the integral from 0 to pi/2 sine squared phi d phi, which is the integral from 0 to pi/2 sine phi times sine phi d phi. So it's the same story as what we had before here. This is a function that is a product of other functions, and when that happens, the triple integral decomposes into a product of 3 single integrals, which we can solve. So I end up with the integral rho cubed, the integral sine theta, and for this one here, sine squared phi, that's a trig identity, that's 1 minus cosine 2 phi divided by 2. That's the only change that happened from this line to this line. We're going to talk about how to remember that trig identity in just a second. Right now, we're just going to crack the integral. And that gives us, well, the antiderivative of rho cubed is 1/4 rho to the 4th. The antiderivative of sine theta is negative cosine theta. And the antiderivative of 1/2 minus cosine 2 phi over 2 would be 1/2 theta minus sine 2 phi over 4. So 1/4 sine 2 phi, right, from 0 to pi over 2. And when we work that out, well, 3 to the 4th is 81, so 81 over 4 minus 0. Then we have negative 1 minus 0, so that would be times negative 1. And then here we have that at 0, theta as well as phi as well as sine 2 phi are equal to 0. And at pi over 2, we have that this is pi over 4, and sine 2 times pi over 2 is sine pi, which is 0. So we end up just with pi over 4 here. So that ends up being minus 81 pi over 16. And that is indeed what it is. Now, the negative sign might make us feel kind of strange, but remember, we are integrating y over a dy that ranges over negative values. So this integral really ought to be negative, right? Okay, what else do we have? Well, yeah, right. The sine squared in terms of sine 2x or cosine 2x. How do I express that? Well, basically, that is a trig identity that, of course, people want us to remember, but how can we do that? Well, typically, I would always recommend that you draw yourself a sine function and you realize then that sine squared is the same thing, only that the amplitude has been cut in half because now it oscillates around y equals 1/2, and we have that the frequency has doubled because here we need 2 pi for a full period, whereas here we only need pi for a full period, which already gives away that we need a doubled frequency either for a sine or for a cosine, and the rest just comes off the picture. Sine squared x is equal to 1/2 because the amplitude is 1/2, and then we're oscillating around y equals 1/2, so we need 1/2 times 1, and then if you now draw another axis in here that is y equals 1/2, well, then you end up with a negative cosine, so that means you end up with minus cosine 2x, and that's exactly the trig identity that we used in the previous panels. So this was a quick review of something that we have done in trigonometry, and it certainly flows very well with the basic philosophy that we had for integration, which is you visualize, you interpret the visualization, and you get the equation from the visualization. We move on and we talk about physics now. Let's compute the center of mass of the solid ball x squared plus y squared plus z squared less center equal than 9, with the density function rho tilde being z plus 5. And so here, of course, we have a clash in notation, which is that in calculus text, typically the radius in spherical coordinates is called rho, but of course rho is also the density. So I'm going to call density functions rho tilde here so that there is no confusion between the two, so they are not being accidentally interchanged. Well, this is basically a straight computational problem because I think we can all visualize what a solid ball looks like, which is also why I didn't have a picture in here. And well, what do we know? We know that the mass has to be the integral of the density over the volume. In order to integrate over a ball of radius 3, the radius goes from 0 to 3. The angle theta goes from 0 to 2 pi. The angle phi goes from 0 to pi. We would integrate our density function, which in spherical coordinates is z being rho cosine phi plus 5. And then we have the rho squared sine phi d theta d rho. And well, that is now something that I can break up. And so on one hand, I get the whole triple integral of rho times rho squared, which is rho cubed, cosine phi, which is here, sine phi here, d phi d rho, d theta d rho. And here I have the triple integral over the same thing of the function 5. But the triple integral of the function 5 over a volume of a sphere will just be 5 times the volume of the sphere. So I transformed back here to just being the triple integral over the ball. And well, now we see something else that is rather nice, and that is that cosine phi times sine phi is 1/2 sine 2 phi, and if I integrate that from 0 to pi, that means I integrate a sine function over a full period, so the integral will be 0 here. So that means this is 0 plus the volume of the ball times 5, so 0 plus 4 pi radius 3 cubed times 5, and so that will end up being one of the 3's cancels. 9 times 5 is 45 times 4 is 180, so this ends up being 180 pi. Of course, a key step here is, and again, this is where we just think about what things mean. When I integrate the phi, well, I could first realize, and that's another trig identity that you want to know, cosine phi sine phi is 1/2 sine 2 phi, as I mentioned before. That one oscillates twice as fast, which means now 0 to pi is a full period, and that means when you integrate that trig function over a full period, you get that 0. All right, so what I want us to keep doing here in order to make this computation manageable is I want us to keep thinking about what things mean, because that will short-circuit some of the computations. Now, I've been preaching for a while already that calculus is about calculation, and so in a worst-case scenario, yes, you can just hammer that computation through and make sure that everything works. But typically, in a face-to-face class, I would often just set this up and then compute it with a computer algebra system. Here, we might as well work our way through the whole thing, because if you want to fast forward through that, you can, and if you want to see how we can manipulate symbols mindfully, then this is certainly a very good exercise in looking at computations and not just seeing symbols, but also thinking about what the symbols mean. So, what else do we know? Well, we know that the center of mass is 1 over triple integral over whatever the region is of the position vector xyz multiplied with the density function dv. And so that would be here 1 over m times the triple integral over the volume of the position vector xyz. Density function is z plus 5 dv. Well, if I integrate over something that is symmetric with respect to the origin, if I integrate a multiple of x, and z plus 5 times x is a multiple of x, if I integrate a multiple of that over a ball, I will get 0 in the first component. Similarly, I will get 0 in the second component, and that is because the x and the y are integrated over symmetric intervals across the origin, and therefore, being odd functions, those integrals go away. So really, that is something, yeah, so those will go away, and that's something we're also going to see in the final setting here. I also just went ahead and broke things up, and that's going to make it even simpler, because when I break this into the integral of the position vector times z and the integral of the position vector times 5, I realize that here I just integrate the positions over the volume, and so these 3 integrals here will all turn out to be 0, because x, y, and z eventually are integrated over a symmetric interval. Similarly here, x and y will be integrated over a symmetric interval, and therefore those integrals go away. The only thing that really stays with us is the integral of z squared. So yeah, this integral ends up being 0, and this integral here, I still kept it, but that gives us, in x we get 0, in y we get 0, and in z we get the triple integral of z squared dv, where here we don't have a cancellation of negative signs anymore, because of course when you integrate z squared over a symmetric interval, you actually get a positive answer. All right, so this was a quick visualization exercise that when you integrate x times something that doesn't turn the x into an x squared or something like that over a ball, you just end up with 0. That also makes sense physically, because what we have here is the density only depends on z. And if the density only depends on z, the center of mass has to be on the z-axis, and that's what the 0 for x and y for the center of mass also say here. Alright, so that means we still need to figure out the integral of z squared dv. Well, that'll be the integral from 0 to 3, 0 to 2 pi for theta, and 0 to pi for phi of z squared, which is rho squared cosine squared phi, times our volume element, which is rho squared sine phi d theta d rho. And again, the highlighting doesn't want to capture the rho here. unless it captures a little bit of the phi also. And yeah, so now that again breaks up into three different integrals, right? We get an integral of rho to the fourth, we get an integral of cosine squared phi sine phi, and we get an integral of 1/4 theta. So we get integral 0 to 3, rho squared is rho to the fourth d rho. We get the integral from 0 to 2 pi d theta, because nothing depends on theta here. And we get the integral from 0 to pi of cosine squared phi sine phi d phi. And that's quick substitutions and quick integrals. We get antiderivative 1/5 rho to the fifth here from 0 to 3. We get 2 pi here, because that's just the integral of 1. And here we get the antiderivatives negative 1/3 cosine cubed phi. That's a quick substitution. U equals cosine phi. And as I've also been borderline preachy for a while, if you don't see that directly, go ahead and use paper and pencil to work it out. Or with the substitution u equals cosine phi, that's a good exercise. Or whenever you read that, at least verify that, yes, when I take the derivative here, I end up with 3 times negative 1/3, so the 1/3 goes away, times cosine squared phi times negative sine phi, and the 2 minus signs cancel to give us really that this thing here is the antiderivative of what we have here. Of course, this is in the boundaries from 0 to pi, and so that means here, let's see, 3 to the fifth, 3 times 3 is 9, times 9 is 81, times 3 is 243, so we end up with 243 fifths, times 2 pi, and we have cosine of pi is negative 1, cubed is still negative 1, so we end up with negative 1/3, and then minus negative 1/3, so we should end up with 2/3 here, and we do. And then we realize that one of the 3's cancels, so we should end up with, that goes back to 81, and then 81 times 4 is 364, so 364 over 5 times, 324, right, 4 times 81 is 324, so 324 over 5 pi, and that gives us for the z-coordinate of the center of mass that this is 1 over m, so 1 over 180 times pi times 324 over 5 pi, and that ends up being 9/25, and that is fairly sensible again because the density gets larger as z increases. We should have a z-coordinate of the center of mass that is in the that is above the xy plane, and then xz equals yz, xc equals yc equals 0. Okay, and yeah, so now we go on and we have a final quick discussion. When we have a general integral given, well, we don't know offhand which coordinate system to use. So let's take a look at this one. We want to compute the integral from 0 to 1, integral from negative 1 square root 1 minus y squared to 0, and integral from 0 to 3 of sine x squared plus y squared dz. Dx dy, well, let us see what we could use here. Our y goes from 0 to 1, our x goes from a negative semicircle to 0, and our z goes straight up. So that looks cylindrical. We also have x squared plus y squared in the integrand, so that also points in the direction of cylindrical coordinates, and so we should probably do that. And so then from where to where do things go? The radius will go from 0 to 1. Y goes from 0 to 1. X goes from negative square root 1 minus y squared to 0. That would mean that we're sitting in the second quadrant, so that means the radius goes from 0 to 1. The theta goes from pi over 2 to pi. Z still goes from 0 to 3. We get sine r squared, and then we have r dz d theta dr, which is the volume element. And of course the really nice thing here is that now we can do a substitution, and so we end up with, well, the rest being computation, of course. We end up with integral 0 to 1 sine r squared r dr, and integral from pi over 2 to pi d theta, integral from 0 to 3 dz, because all the other stuff doesn't depend on their respective variables. The antiderivative here should be negative 1/2 cosine of r squared, which is indeed what it is, negative 1/2 cosine r squared from 0 to 1. And then here, of course, we get pi over 2, and here we get 3. cosine r squared at 1 is just 1. So we get negative 1/2 cosine 1, and we get minus negative 1/2. And so that means if we pull the 1/2 out, we end up with 3 pi over 4 on the outside, and then 1 minus cosine of 1 on the inside. And that's approximately 1.0831, which is also something that you can verify with a computer algebra system if you plug that in. Okay, so we can work out these computations fairly nicely here. And finally, then, the typical question is, whenever you are faced with something that has curved boundaries, when do I use which coordinate system? And there really are no hard and fast rules. So what you want to think about is you want to think about the following and verify that it makes sense. Don't memorize it as the thing to do, even though it's pretty much a good idea to check this first. Namely, when you've got cylindrical symmetry of the domain, or terms x squared plus y squared in the integrand, that typically is handled with cylindrical coordinates, whereas when you've got spherical symmetry of the domain, or terms x squared plus y squared plus z squared in the integrand, that is usually handled with spherical coordinates. Now, you could set up something that has spherical symmetry in terms x squared plus y squared, because of course that's something you can model in spherical coordinates. You can probably also go conversely. Things would just get more complicated, but usually it's at least a good idea to first check these coordinate systems in these respective situations. And with that, we are through with most of the ugly triple integrals that we can set up, because the only thing that could get worse is that we actually would need to use a coordinate system, a coordinate transformation, which is a whole different ball game. For now, we are done at least with the strict geometric setups, and that's probably not bad also. Enjoy solving some integrals in cylindrical and spherical coordinates.